Loading. Okay, great. So welcome everybody. So it's a great pleasure today to have Richard Montgomery, who will talk about his great solution of problem of Erdős and Hajnal. It's actually several problems. Like my favorite one would be about cycles which have lengths which are powers of 2, but Richard will tell you more. Please, Richard.
Thank you very much. Thank you for the invitation, Benny. It's lovely to be in Beijing virtually, at least. Okay, so as Benny says, I'm going to talk about Erdős and Hajnal's odd cycle problem, but really a collection of problems about the length of cycles. And this is all joint work with Hong Liu, who you can see has joined us. Hi, Hong, who's now at IBS in Korea. So this is all about the length of cycles. So really, this talk is on two main problems, and we're essentially trying to say something about the cycle length in a graph with as little information as possible. So firstly, given the average degree, which I'll denote D of G, of a graph G, what can we say about its different cycle lengths? So there, all I'm interested in is if a graph has a cycle of length 3, if it has a cycle of length 5, something like that. I'm not worried about the number of different cycles. And then the second question is, given the chromatic number phi of G of a graph G, what can you say about its different odd cycle lengths? So in order to help us there, let me bring up, okay, so I'll just denote by this lovely calligraphic C of G to be the set of L such that the graph G contains a cycle of length L. And then as I'll talk about an awful lot, there's a big difference between even cycles and odd cycles, like so many things in graph theory. So I'll put odd in the subscript just to pick out the odd cycle lengths of a graph. And my two questions are a bit vague. What would we say about its different cycle lengths? So the talk is going to talk about kind of 4 different things. We're going to talk about some notion of density of the possible cycle lengths of a graph G. And similarly, some notion of density of just the odd cycle lengths of a graph G. And then we'll also try and find some cycles with specific lengths. And again, some odd cycles of some specific lengths. So those are the 4 sort of main things I'll be talking about. So first of all, what might we mean by the density of the different possible cycles in a graph G? So it's easy to show, as long as the I guess you have average degree at least 2, that the number of different cycle lengths that you should be able to find in a graph G is at least linear in the average degree of a graph by passing to some minimum degree subgraph and say looking at the longest path and what edges you must find back into that path. Okay, so that's what we know about the number of different cycles, and obviously that's tight considering a complete graph. So in 1966, Erdős and Hajnal suggested this function here on the left as some measure of the density of the cycle lengths in a graph. So specifically asked, if you take the sum of the reciprocals of the cycle lengths, is that forced to go to infinity as the chromatic number of a graph goes to infinity? And like some of these problems that appear quite a bit in the problem papers of Erdős, it's a little unclear, but so perhaps later they then suggested that maybe just having a large average degree should be sufficient for the sum of the reciprocals to go to infinity. Okay, and maybe let's note here what might this for sum of the reciprocals function look like. So if we just focus on the average degree, then note that for complete bipartite graphs, KDD, and we think the sum of the reciprocals from the possible cycle lengths go from 4 up to twice d. So the sum of those reciprocals of all those integers would be log d, but we're only getting the even ones. So our sum is about 1/2 minus some little error term times log d. And certainly in 1975, it's written down, Erdős conjectured that this should be an asymptotic lower bound for graphs with average degree D. And we do have some good progress on this problem already. So in 1984, the Arfish combination summary proves that you don't need a large chromatic number at all. All you need is to have a large average degree, and some of these reciprocals will go to infinity. And they even proved you get the right order, the right lower bound. So they proved that some of the reciprocals is at least linear in the logarithm of the average degree of the graph. And again, looking at the complete bipartite graph, that's the best order you can expect. But maybe we can try to improve this implicit constant within here. So really this, let's see. Okay, so this is, if you remember on my last slide, this is some measure of the density of the cycle lengths in the graph. And I also want to consider whether you can find specific cycle lengths in a graph by imposing an average degree condition or a chromatic number condition. And it's really well known that Erdős proved that if you fix some k, we can never guarantee that a graph has that a cycle of length k just by imposing a chromatic number condition, and of course definitely an average degree condition. So instead of looking for a specific cycle, can we say that there must be one of a sequence, say sigma 1, sigma 2, sigma 3, appearing in the cycle length? So this is the question, for example, of the form that Benny mentioned at the start. Can you find a cycle whose length is a power of 2 in a graph, just by imposing some average degree condition or chromatic number condition? Okay, so just to kind of, while I've brought a little more clarity to it. So given the average degree, I want to ask how dense can you have this set of cycle lengths? And also ask whether the set of cycle lengths contains maybe some specific sigma I in some sequence. And then, as I mentioned, of course, even cycles and odd cycles behave really differently. So obviously, complete bipartite graphs, we can get a very high average degree, and we're still getting no odd cycles at all. So instead of an average degree condition, let's try a chromatic degree condition. So if I give you the chromatic number of a graph, can you say something about the density of just the odd cycle lengths of the graph? And can you do the same thing? And can you say it must contain some sigma I if I give you some plausible sequence, sigma 1, sigma 2, sigma 3? So now in the next slide, I'm going to sort of blow up those 4 questions a bit and give you really specific examples of what I'd like to answer. So same information as was on the previous slide, but just a bit more space. Okay, so I've already talked quite a bit about the average degree of a graph and asked about how dense the cycle set is. And it was proved by Arfish combination summary, as I said, in the 80s, that if you look at this function suggested by Erdős and Hajnal, that the sum of the reciprocals, it grows at least like some constant times the logarithm of the average degree graph. And then really the only improvement we might expect to be able to make is this conjecture of Erdős, or this question of Erdős, which asks whether we can prove the implicit constant to asymptotically 1/2.
So Richard, in all this question, you're saying average degree, but substituting it with minimal degree, it's the same because your formula's insensitive to these constants, right?
Exactly. Because we're taking logarithms on each side, yeah, dropping a factor of 2 or 4 or whatever it is and looking at minimum degree. Exactly. We can also assume as well, using the standard ways, that we're a bipartite graph as well. So this is really a question of bipartite graphs and even cycles, which is why I put even cycles at the top here. Exactly. And so here we go. Here is some very specific example, and it's exactly the question Benny said at the start of this question of Erdős in 84, he had written down, is there some D that just says by having average degree at least B, then a cycle, a graph must contain a cycle length, which is a power of 2. So I will mention at the end, eventually it does start to matter average degree or minimum degree if you're, for example, want to know the absolute best possible D here that could give you this question. But at this moment in time, we would be happy with just some constant D. So I'll keep it there. So that sort of recaps and makes explicit the questions I had on even cycles. So if we now take and look at odd cycles, see, here's the question of the title of my talk. And it's a question of Erdős and Hajnal from the 80s. And it's, if we look at the same function as a function of the density. So if we take the sum of the reciprocals of just the odd cycle lengths now, does this go to infinity as the chromatic number of the graph goes to infinity? And I put my title, I know Benny prefers the power of 2, and put as my title of the talk because it really uses all of the work that we did on this. It builds up to it, as you'll maybe see. And then there are no real specific questions I think we could find about specific sequences, but we could similarly ask if we impose for example, some high chromatic degree condition here in the bottom right, must we get a cycle whose length is a prime number? These are the questions I want to consider, and let me tell you now the work that Hong and I did on this. Okay. So first, I'll give you a little more background on the average degree and the even cycle lengths, because there was some previous work on that. So a quick definition, we'll say a sequence sigma 1, sigma 2, sigma 3 is unavoidable with high average degree if there's some D such that if we have average degree, at least that D, then we must have one of those entries in the sequence as the cycle length in our graph. So in other words, my question on the previous slide is the powers of 2, are they unavoidable with high average degree? So what can we say? So we have an early result of Bullebash in the 70s that says if this is an arithmetic progression containing even numbers, then it's unavoidable with high average degree. So obviously, again, we need to be even numbers. And that's really quite a dense sequence compared to ones we want to consider. So in 2005, Verstraete showed that there is some increasing sequence with density of 0, which is unavoidable with high average degree. And you can maybe guess from the wording there, it's a non-constructive proof. So it just shows that some such sequence must exist, and also therefore inherently lots of sequences. Okay. So that was in 2005. And then there's work by Benny and again Jacques Verstraete from 2008, which shows that if you have an even increasing sequence, which is exponentially bounded, then it's unavoidable with high degree in all graphs except really very, very, very sparse graphs indeed. So as long as the average degree isn't less than the exponential of log star of the number of vertices in G, where log star is this really slow growing function, the number of times you need to take the logarithm before you get below 1. And for exponentially bounded, that just means there's some constant c bigger than 1, such that you can bound the subsequent term by at most c times the previous term. So these are much sparser sequences than arithmetic progressions or anything like that. And indeed, they include the 2 sequences that we had before explicitly, the powers of 2 and the prime numbers. And we know that it's unavoidable except for perhaps these really, really, really sparse graphs. So if you want to make any progress on those questions from what we knew in the 2000s, then we need to do so with the techniques that work on really, really very sparse graphs indeed. Okay, so here's the work that Hong and I did on this question particularly. So I think I put 2022 because it definitely appeared on an early view online in the journal. I think maybe it will be formally eventually published this year. Anyway, so what we were trying to do was construct cycles with some control over the length of those cycles. And we, after a long time, managed eventually to do this well enough that we could find a large interval in which we could construct any even cycle length. So specifically, we proved that there's some d naught and 0 such that if your average degree of the graph is d and is at least d naught, then you can find some integer r, which is at least almost d minus divided by some polylogarithm of d. Then you can find an interval from log to the 8 r all the way up to r, such that the cycle, that the graph contains a cycle with length every even integer within that range. So I will talk a little bit about our proof later and how we did this construction. And then it'll probably, this theorem will make more sense that we construct lots of different cycles, and then we can vary the length slightly. And that means we can hit every even integer within some interval. And obviously this is for some r, so we can't tell you which interval, obviously, we're going to hit. But we will manage to hit this quite dense interval. So let's see what it says from on the previous questions. So first of all, we know we contain every even integer in that sequence there. If we sum the reciprocals in that interval, then we get around log r. And then we're only hitting the even ones, so we get about half of that. So we get this lower bound that for some r, which is at least d over this polylogarithm in d, we get at least 1/2 minus some error term times log r. And then because, again, log d is close to log r, we get this lower bound that was that Erdős asked about, this 1/2 minus log d. So that's good. And then also we care about these sequences and whether we can pick out sequences. So what we have directly from this theorem, therefore, is that if we have any even increasing sequence, sigma 1, sigma 2, sigma 3, that eventually appears in each interval, log 8 of r to r, for all r is 1, then it's unavoidable with high average degree. Right, so we know we can hit every even integer in each of these intervals. In one of these intervals. And by making d large, we can make r large. So therefore, if we eventually hit each of these intervals, then it's unavoidable with high average degree. So in particular, if an even increasing sequence, sigma 1, sigma 2, sigma 3, is exponentially bounded, then is unavoidable with high average degree. And we can really do sequences that are quite a bit sparser as well from that. And I'll talk about the limitations of this at the very end. So this is our result on even cycles and then the implications on it. So there's a little bit of work, on chromatic numbers and odd cycle lengths. So here's a very similar definition. We'll say a sequence is unavoidable with high chromatic number if there's some k such that if the chromatic number of graph is at least k, then I must hit one of those cycle lengths. On my previous question slide, it is are the prime numbers unavoidable with high chromatic number? And maybe slightly less known about this. So Philip in 1992 proved that at least we can get lots of different odd cycle lengths. So more specifically, if the chromatic number is at least 2k plus 1, then we get at least k different odd cycle lengths in the graph. And then again, Sudikov and Verstraeten. So what he proved, Jacques, was that again, you can actually find consecutive integers, which is a really nice thing. So if the chromatic number of a graph is at least k, then it must contain at least a linear number of k consecutive integers. And then the best result we have towards this odd cycle problem, Erdős and Hajnal, was by the same authors in 2011, who proved that the sum of the reciprocals of the odd cycle lengths does go to infinity if the independence ratio of G goes to infinity, not extremely slowly compared to the size of G. So where I won't state the independence ratio, but some relaxation of the chromatic number of G. So there's some work there, and again, it's really hard to deal with the sparsest graphs. It's really where our work has to come in. And here is my work with Hong on this from the same paper. So it's a really similar result to the previous one. Instead of average degree, by imposing a large chromatic number condition, we're going to find an interval in the graph in which we can find every odd integer instead of every even integer. The interval we're getting is not quite as good. So the statement exactly says there's some for each epsilon, some k naught, such that if we have chromatic number k, which is at least that k naught, then for some r, we're getting every odd integer in the range from r up to r times k to the 1 minus epsilon. So by making k really large, we can make this k times 1 to the epsilon really big. So in particular, let's look again at these some of the reciprocals in this. So we get some of the reciprocals of 1 over L. We get that it should go to infinity as the chromatic number goes to infinity. But not only that, we get the best possible asymptotic lower bound here. So again, if we sum the reciprocals in this sequence here, maybe I should have written about, so the log r's will cancel, and we'll get this 1 minus epsilon times log k. And again, I'm getting the odd integers here.
So Richard, how we need to think about this? So R is fixed, K is large, right? What is so we want as a function of K, right? So we're fixing R.
Right. So we don't actually, we're not fixing R, we're just saying some R exists.
Yeah, right. That's what I mean. But it's a bounded R, right? Where K is very big, but R is somewhat bounded.
Not necessarily. So for example, in really sparse graphs with n vertices, K could be maybe just something we've taken to be large, and then R could be log n, something like that. Or it could be some polynomial in n.
Right, but then, right, if you add reciprocals of, right, so imagine your R is much bigger than K. If you add reciprocals, then you're not going to get maybe still, right? Still you're going to get log K. Yeah, right.
Yeah, exactly.
Because you get the ratio, log of the ratio. Okay, so it really doesn't matter what the R is. Okay.
Yeah.
Excuse me.
Because it looked right, but because you have this extra K, even if K is smaller than R, you still, as long as K tends to infinity, regardless of R, you're going to get logs. Okay.
Exactly. So I've left it out, but if you're watching, I'm sure you can do the little calculations. So exactly, so the sum of the reciprocals up to R times K to the 1 minus epsilon is about, the odd ones is about 1/2 log R times K to the 1 minus epsilon. And then we've got to take away log R, well, 1/2 log R for the start of the sequence. And all cancel out and give us what I have here.
Excuse me, is this R related might depend on also k and this k, but not necessarily k naught, or
so there's no lower point, so the r could genuinely be 1 in what we have here. So it's just any r, and then it will cancel out in this logarithmic calculation below.
no, I'm not saying the calculation. I'm saying for some r greater than or equal to 1, this r dependent on k or k naught, or
the r is depending on the graph. For a different graph, you'll get different r's. So for example, if the graph G is a complete graph, then we'd expect r to be very low, and you could find every odd integer from 3 up to 3 times this k, and the k will be large then. But then if you take a sparser graph, so if you look at the Erdős probabilistic constructions, then you'll come up with graphs with n vertices, chromatic number k, which don't have any short cycles, so this r will need to be at least log n. And indeed, in our constructions, it would come out as, I don't know, maybe log to the 8n, or some logarithm, larger logarithm in n. Yeah. So it very much should depend on the graph G. Does that make sense?
Yeah.
Yes. Okay. Thank you.
Okay, so I have just one last implication of our work. So again, the exact same thing. If we have an odd increasing sequence, which is exponentially bounded, then it's unavoidable with high chromatic number. So this one is maybe easier to see. If the sequence is exponentially bounded, then we just need k to the 1 minus epsilon to be bigger than c, where c depends on the sequence, to mean that we hit this interval of odd cycle lengths that we're constructing. So let me just recap the sort of results of our work, and then I'll try and say something about the methods. So this is a slide I had previously. Okay, this work by Gerfers, Commosh, and Semerity that we're now able to confirm this question of Erdős. So that is indeed 1/2, some things. And then this question here, we definitely like to be able to have come up with a better D, but certainly with high average degree, then you are forced to have a power of 2 as your cycle. This odd cycle problem, it's true, this does happen, and the growth rate is at least logarithmic in the chromatic number of the graph. And again, it would be nice to do better on the k, but we can't, but indeed, there is some k, such if you have average chromatic number at least k, then you do get a cycle with a prime number length. And indeed, in both cases, we can do a sparser sequence indeed than these. Maybe it's a good point to ask if there are any questions about any of that. Otherwise, I'll talk a little bit about our methods. Okay, I don't see anything to hear anything, so let me proceed. So definitely, as I said, so Benny has this really nice work with Jack Verstraete that works well on denser graphs. And in general, if you have a very dense graph, say, then it's pretty easy to play around with your cycles. So we really want methods that are going to work on sparse graphs. Okay. Here's some bits of the proof. So we're going to use a constructive approach, and our constructive tool that we're going to use to create these cycles is going to be just connecting pairs of vertices with paths that aren't too long, so with relatively short paths. And we're going to build some structures to allow us to adjust the lengths of cycles. Okay, so I have some pictures of our what we'll be constructing in a bit. And as I said, we need to work in very sparse graphs, and that's really the challenging case. And to do this, we're going to use a form of expansion introduced by Commosh and Semerity in the 90s to find and they were finding subdivisions in sparse graphs. And this is a form of expansion that's been really very useful, especially recently in the last 5 years or so. It's really useful if you want to find structures in exactly this, in very, very sparse graphs. So if you're just imposing some average degree condition that might be some large constant, then this is a very weak condition. There's not very much that we can do using this, and this expansion is probably the most sophisticated tool we have to approach this. So let me give you a quick okay, so first of all, as Benny says, we can assume that we have some minimum degree condition, which is good, very standard. In all the results I said, you'll note it really doesn't matter if we slip by a factor of from d down to a factor of d/4 or something. So using the standard way, we can assume G is bipartite and has a good minimum degree condition by passing to a subgraph with those properties. Okay, so for the rest of the talk, I'll talk a little bit about constructing our even cycles in a simplified setting. And I'll put off saying anything technical about the common or summary expansion until after that. And then finally, I'll say something about finding odd cycle lengths from this, and then cover a little bit the sort of limitations of our methods at the very end. Okay. So let's think about constructing even cycles, where what we really want to do is develop some control over the length of the cycle that we're constructing. So let's take a simplified setting, and what we want to really do is just to be able to take two vertices and find a path with a specific length between those two vertices, say x and y. And then if we can apply that with an edge in the graph, then we'll get a cycle with this specific length. Okay. So this is our aim. And then for the simplified setting, let's assume that we can find between these two vertices, instead of a path with a specific length, just a path that is reasonably short. So this, as you'll see, might be if G has n vertices, then at most some polylogarithm in n. And let's assume that we can do this vertex disjointly between lots of pairs of vertices and see where we can get to with our construction. Okay. So just to give you something a little more concrete, if we have n vertices, let's say we can connect pairs of vertices with paths with length at most m, where m is around log cubed of n. And let's start with these vertices x and y. So I can definitely, using this, I can pick two other vertices and connect them twice with paths of length at most m, and I'll get a cycle with length at most 2m. And now if I apply this path connection property again, I can connect this, and I connect x and y to almost points of the circle, vertices of the circle that are almost opposite, but not quite. So this will be an even cycle because we've assumed G is bipartite. And what you can note in this little diagram here, that there's some L for which I can find an xy path in this diagram with length L and with length L plus 2. So all I need to do is either go the short way around this circle or go the long way around this circle. So by switching between those two options, I can adjust the length of my path by length at most 2. I think, are you talking, Benny, but you're muted?
Sorry, but you need them connected to the cycle in a very specific place, right?
Exactly, yes. So a very specific place. So take the two opposite points in the cycle and then move one vertex down one. Yeah. So the property we have is I can take specific pairs of vertices and connect them with paths like this. All vertex disjointly. So into that property, I just plug those two vertices that are to be connected, and connect them on. So I'll say more later about how that property comes relatively naturally from expansion. Okay, so this gives me a little tiny bit of control. I can adjust the length of my path just by 2. So now all I need to do is to do a similar thing, but connect lots of these cycles in. And I'll be able to do lots of little adjustments, and this will add up to give me a bigger adjustment. Okay, so here's a recap of what we can do. We can connect pairs of vertices with length 2. Sorry, with length. We can make pairs of vertices, vertex disjointly with short paths. Length from this m. Okay, so now if I have this property, let's take some L, which is some polylogarithm in n. And by doing the previous slide lots of times, you can find a path between vertices with length either L or L plus 1. So this time, instead of saying some L exists, I'm saying for this specific L, we can now find a path with length L or L plus 1, depending on the parity in the bipartite graph and which side X and Y are on. So to do this, if we take M vertex disjoint cycles, then we can join them in a path from X, like so. So these cycles have different lengths, probably, but I can do the same thing, take almost opposite vertices and join them in a path like so. And then I extend this. Okay, so let's take the shortest path through these to start with. And then we're aiming for a path length L. So using this connection property, I can keep picking a new vertex like so, and joining it with a path of length at most m. Okay, so using this, I can extend the length of the path in sections with size at most m. And I extend the path until its length that goes through the shortest loops of the circles is within L minus 2m and L minus m. And now I can connect the end of that path to m, to x, with a path of length almost m. So in the third bullet point there, that means this blue path has length between L minus 2m and L. And now we have the control that we can lengthen it in bits of 2 by flipping up the paths, like so. And I can do this up to m times. So all we need to do is lengthen it the right number of times until it has length L or L plus 1. So again, we can't hit exactly L. We're only lengthening by 2 each time, but we can hit either L or L plus 1. And that will naturally be one of them, depending on where X and Y lie in the bipartition of the graph. So this is my adjustment, and it tells us we can get L or L plus 1. And essentially, I've done this for L is equal to log to 10n. But all that really mattered was this was at least a certain length, so that we could fit in enough of these cycles within this path and still end up with something that was shorter than L. So if we can get this property where we can vertex disjointly connect lots of paths, then for lots of different values of L, we can apply this and find a path of that length. So where do we get this property from? We get this property from Combinatorics summary expansion.
But just to understand, so far L is much bigger than M, right? So it looks like it's a very modest progress, right? Because you in the aim for interval which is much longer than the beginning thing, right? So here, this M, getting M consecutive things, M is only low cube, but L is really big still.
Right, yeah, so within this, yeah, I am also not just getting a path of length L or L plus 1, probably I am getting some different consecutive order lengths as well. Yes. So that's not so much the important point. So the important point is that this works for any L that's at least log to the 10n. So if the path starts to occupy too much of the graph, then it will be a problem. But in the expansion graphs that we're doing this in, essentially we can do this for L is log to the 10 over n up to, I don't know, maybe square root of n, something like that. So yeah, so the point is not that this construction gives us m different lengths, though it does, m plus 1. The point is it works for a far broader range of paths than I have L here. So once we find this adjustment, we can really keep extending this shortest path to be really very long before connecting it to y. Yeah.
Okay.
Does that make sense?
Yeah, maybe I'll see next.
So it's a bit vague because I haven't really stated the exact conditions and so on. But in the background, this really does let us find a very large number of cycle lengths. So to say a little bit more then about this connection property, we get this from expansion. So let me reintroduce the Montgomery expansion from the 90s. And this is a sort of corollary of their work, but just to give you an example that this connection property naturally is used in this work, they proved that every graph G contains some subgraph H in which every pair of vertices is connected by a path with length at most, this beautiful thing here, so it's the most order of log cubed the number of vertices in H, say. Especially if we're looking at sparse graphs G, where as I say, the important cases where G is really very small. Okay. So in order to do this, what they do is they prove that it has a subgraph H, which has some expansion or T. And here the expansion is a little bit technical, but so don't worry too much about the constants and all involved in here. What we want to say is that a graph is an expander if for every set of vertices U, which is neither too small or too big, if we look at the neighborhoods, the external neighborhood, the vertices n of U, a set of vertices n of U, which have some neighbor within U, but aren't in U, then the size of that neighborhood must not be too small. And there are lots of really nice expansion properties which you can use to prove things. So for example, lots of sort of pseudo-random properties that say Benny was using recently to construct Hamilton cycles. We use expansion conditions where the neighborhoods are much bigger compared to this than the size of the set of vertices. So here, unfortunately, our expansion can be really small. So the expansion coefficient here is epsilon divided by some log squared, 15 times the size of U divided by K. So whenever U is quite big, if it has the same number of maybe the size of H over 2, then this expansion is small, and the neighborhood is guaranteed to be some size, but smaller than the size of U. So we think of this as sublinear expansion because of that. So the bad point is that it's a really weak property to work with, which makes it a real pain. The good side is that, as Commerce and Shitty proved, that as long as we impose a sufficiently high average degree condition, then we expect to find within any graph G that it contains a bipartite graph which expands in this very weak sense. And then we also have a nice minimum degree condition as well. So by dropping a factor of 8 in the average degree, we get some expansion property as well as the more normal minimum degree property. So it's a very weak expansion, but we can find it in even incredibly sparse graphs. So the challenge is to try and take this weak expansion and do the construction essentially I showed you on the previous slide. I won't say too much about this because it's a bit technical, so I defer to paper for that. We really tried to emphasize the really key technical bit that helped us actually manage to do this. But here's just some indication of why expansion is good for us. So if we do have these pair of vertices x and y, it'll look a bit strange if I swipe aside. But if I look at the set of neighbors of x and y, that comes from the minimum degree condition. We know that each of these have the neighbors. And once we've looked at that, we can then start applying the expansion condition to show that these neighborhoods are growing in size. So we have these wizard hats, and eventually these will overlap within the set, and I can find a path of here length of something of the order of log cube n. So in a nicer world, these neighborhoods would double in size, and these paths would have log n, but because of the log squared 1 over log squared term, we might have to go out log squared times before we double in size. Okay. But we're still managing to do what we want, but just for 2 vertices, and we want to be able to do this lots of times. Okay. So in an n vertex expander H with minimum degree at least d, just to sort of naively using the expansion as I outlined just above on the slide, we can only connect around of the order of d arbitrary pairs. And the construction I showed, it was connecting at least m circles together, where m had length was around log cubed m, because that's the length of my upper bound and the length of my points. So this is why it's harder than it might otherwise be. So a few notes on how we managed to get around this. So this part of it is a relatively common idea. So instead of finding cycles, we find what we call adjusters. So the problem is if we find lots of cycles, then we're trying to connect pairs of vertices x and y, and that's hard to do because they might have no neighbors other than inside the stuff that we're trying to avoid. So we'll find cycles, instead of these for just these vertex x and y, we find at the same time some large subgraphs x and y stuck on, which have relatively low diameter and which are quite large compared to the cycle C. So in particular, if the size of x and y is much bigger than C, then we can do this expansion instead of x, the vertex x around the set x. And that way we can avoid the rest of the vertices of the cycle. Because as Benny noted, we really want to connect very specifically x and y. So if we expand x, but you use in those paths other vertices in the cycle, then it will ruin everything. Okay. But if we have these large sets, x and y, and then we can expand those while avoiding the cycles, or maybe other cycles that we've connected, and then connect those up. So we can use the construction that I outlined, but instead of the cycles and vertices being connected, we use these adjusters. And then finding many vertex disjoint adjusters here is the main challenge. So
Richard, when you say many, you mean how many?
So it definitely is logarithmically many. So we want m of these really to connect together. We could find, say, square root of n of them. In general, something like that. But definitely we need at least polylogarithmically many of them in order to do the construction I find. So I'll say nothing more about finding them, but
maybe just question. So just to achieve this, right, your initial set of cycles should be a little bit far from each other, otherwise, right?
Yeah, exactly. So there's an awful lot of saying, okay, assume you find these vertex adjusters, put them together into a vertex set, and then look somewhere else in the graph. And as soon as you start doing this, then you've got to consider cases. What happens if you have large degree vertices? So maybe you can't look far away in the graph.
Right.
And again, as you say, it's, well, sort of indicate the difficult cases are usually when you don't have many large degree vertices to play with, and in that case, yeah, you want to step as far away from the stuff you find as possible.
Mm-hmm. Okay. Yeah.
So this was all about finding even cycles, essentially, so far. So here's how it can be applied to odd cycles. So from all the sort of work I was sketching out, we get a more technical statement here. And so if you find an expander subgraph using this result of convolution summary, and then apply this construction that I showed you with these adjusters, what you get when you put this all together is to be able to say if your average degree of graph is at least D, then you can find some connected bipartite subgraph within it, and some L, such that for each distinct X and Y, and each integer within this interval here, there is some XY path with length R and H, if parity permits. So it's a bipartite graph. So if you're asking for something reasonable, a even length path between vertices in the same side of the partition, then you can find it if its length is within this interval. So I've slightly simplified things. So if you really push what we did, you get the interval I showed you earlier with even cycles. And then just for the odd cycle stuff, we just need to consider this interval. So you get this slightly smaller interval. So you want to take this and do something with it for the odd cycles. So here's what we do. Suppose you could find the following cycle of bipartite graphs, H1 over H5. So we want to repeatedly apply what I showed you in some way and find my 5 bipartite subgraphs, H1 over H5, which intersect only on these vertices I have here, the small black circles, so that they each satisfy that condition. So for distinct pairs of vertices, so there's some Li which varies according to the Hi. So that for pairs of vertices, if you give me a reasonable cycle length that's odd or even within this interval, then there's an XY path with length R in Hi between those. So the natural thing to do is to apply this property to each subgraph H with these pairs of vertices now within this cycle. So if we just find, if we could find a path just on a cycle just on these vertices, it would be a 5 cycle. So if we now replace those edges by varying odd numbers, then we'll get many different odd cycles. And that's essentially all you need to do. That's essentially the idea behind it. In reality, things are a little bit more complicated because these subgraphs may intersect on more than one vertex and so on. So I think I've sketched out just a little bit. So that's the result that I had. Again, the upshot of all our work. So given some high chromatic number, we want to iteratively find as many edge disjoint connected bipartite graphs, EHI, satisfying that box property. And then from that result, we know that the union of those graphs has chromatic number at least 3, and therefore it contains an odd cycle. And just very roughly, if you take a minimal such odd cycle, then you might not be able to replace all of the edges, but you replace enough of the edges using the box property to create many odd cycles. So it really does look like this, but you're maybe varying half of the edges around the basic underlying odd cycle. And you have to express what you mean by minimality in the right way. But once you've had this idea, I don't think it's very hard to follow through to find these different odd lengths. So let me finish just by mentioning some of the limitations of our methods. So with convolution summary expansion, these paths, as I said, might have length up to around log cubed of m. So if you follow this through, how fast an increasing sequence can we deal with an even sequence? So I just stated it for exponentially expanding, so expanding by almost some constant multiple each time. Actually, we could cope with this statement here where a third is replaced by, say, a tenth or something like that. And we didn't push to get the best possible thing there, in part because with our methods, the best possible you could hope for, because of that 3 becomes this 1/3. So the best possible you hope for are sequences that increase the speed. The next one is the most exponential of the cube root of the previous one, and say it's unavoidable at high average degree. But if you, again, look into the constructions of Erdős on having graphs with no cycles up to around log n, and they have n vertices, it seems reasonable there might be some upside on such any increasing even sequence, which grows really quickly. So at most, a subsequent term is at most exponential in just some epsilon times the previous term. So maybe that even sequences that grow as fast as that should be unavoidable with high average degree. And then just to say that, okay, we proved if a graph has sufficiently large average degree, then it contains a cycle whose length is part of 2. We're really far away from doing the best possible here. So there's a conjecture of Erdős and Hajnal that every graph with minimum degree at least 3 should contain a cycle whose length is a part of 2, which seems well out of reach of our methods. Okay, so I'll wrap up there. So thank you very much for your attention.
Thank you, Richard. So for a very interesting talk. So about the question which you mentioned, so in the paper with Jacques, we have some construction which shows probably maybe a bit more than that, if you change sigma I power 1 to something slightly bigger, then it's already just not true.
Right, yes.
So at some point, right, like this thing stopped working, right? So with constant degree, right, you cannot find sequences which a bit.
Exactly, yes. But I think that follows from, so if you have some large average degree D, it's just a large constant D, then aren't there graphs with n vertices, average degree D, which have no cycles of length log n? Possibly log n divided by something.
But log n over log d, right? That's the best what you can hold.
Right, log n over log d, yes.
I see.
Right.
So you're saying that the sigma I to the power 1 is the best you can hold, right? Or
yeah, definitely. Definitely that. But maybe you're right that maybe epsilon as a function could even go to 0 as the average degree is getting big. Yeah.
Okay, I look, I don't remember what, but it's interesting, I see. Right. Yeah,
I should look up again. I'll look up your paper again. To be honest, we didn't think too much about it because our methods are so far from being able to do that.
Yeah. Other questions?
Hi. So could you mention again what's the difference between the cycle and the adjuster?
The cycle and the adjusters.
Yes.
Yeah. So the cycle. If you remember, I had the cycle that's then connected by 2 paths. vertices in. These paths connecting the cycle were replaced by triangles. So these triangles are meant to indicate that I've just found some large set of vertices attached to the cycle instead. And that helps me connect the cycle into the next part of the construction. So the construction I had was you take these cycles and you want to join specific vertices on them between different cycles. And this is very difficult to do while avoiding the stuff you've already constructed so far.
Mm-hmm.
So if
why should the triangle help?
So the triangle helps because it has low diameter and a lot of vertices. So the problem becomes I just want to connect any one vertex in the triangle rather than that specific vertex X.
Uh-huh.
And then once you get that connection, you can get rid of most of the triangle because it has low diameter.
Mm-hmm.
So you're not setting aside too many vertices to do the next construction.
So is the triangle simply a tree with some kind of big depth and very wide, like very wide tree?
Exactly, yes. Yeah.
So how deep is the tree? Could you give me a?
So the depth will be, it won't be quite, let's say, a binary tree or anything like that, because that's too fast an expansion. So it will be, the depth will be about log cubed n, say.
Okay.
And that will let it to at least expand to some large polylogarithm, much larger polylogarithm in X.
Okay, thank you.
Any more questions? Actually, I look meanwhile, Richard, in our paper. So indeed, we remark that if you change this epsilon to something which is a big constant, maybe growing with I, so then you already, there are sequences which are avoidable.
Right. Yes.
Right.
Yeah.
That's what we're doing, right? So this basically is a border how far you can go. Right? The power of sigma should be 1, and you can just play with this constant. Yeah,
Exactly.
it's a very plausible conjecture.
And I think
Sorry?
And I think very difficult.
Yeah, it's definitely right to get. I mean, even before your work, even to get just exponential was not so clear how, right? And actually, I think we don't know how tight is this Conlosh-Semeredy method in terms of what's the right powers of the logs there. And I think you need to know all of this.
Yeah. Yeah.
Right.
Okay.
Yeah, it looks like. Okay, any more questions? If not, great. So let's thank